So far in this PyTorch series, we looked at tensors, various attributes and operations. We also looked at important concept of automatic differentiation and computational graph in computing backpropagation as well as derivatives. Then we looked at cost functions and optimizers. Finally, we started with a PyTorch model template where we defined these 8 steps. And using those 8 steps, we did a linear regression end-to-end example and also logistic regression end-to-end example. We also did a 2-layer neural network to solve MNIST problem. And today we are going to look at convolutional neural network and try to continue how to use convolutional neural network to solve the problem of MNIST. So convolutions, I think the basics of these are presented in various tutorials. I definitely found this particular blog post by Belajar and you can see the student notes here, very easy to understand and define very clearly. So I'm not going to go in detail. You can follow Andrew Ng's lecture and also go through this particular blog post to get a basic understanding. So in this case, I'll go through 2 examples. The first one is MNIST example. For example, you start with a 28 by 28 by 1 image, and you are going to do a convolution operation with a kernel of 3 with filter 16, and the activation function is ReLU. So this particular dimension, because of 16 channels, you are going to get a 16 channels and 28 by 28 dimensions. On that, you are going to apply a max pool 2 by 2. So the 2 by 2 will reduce to a 1 dimension 1 by 1. So 2 by 2 will reduce this 28 by 28 into 14 by 14, and you again apply convolutions with 32 channels, and this 16 by 16 by 14 by 14 by 16 will become 14 by 14 by 32 number of filters, and again you are applying max pooling and 7 by 7. Finally, usually in convolutional neural network, once you apply various layers, you end with a fully connected, you flatten it, you do a fully connected network, again you do a fully connected, and finally you output to the number of desired nodes. For example, in this case, in this there are 10 hand digits, so your output layer is going to contain 10. So this is slightly more complicated or more depth, deeper convolutional neural network with many more layers, but again you can see that the end ends by a fully connected layer followed by an output layer. In this case, it's an ImageNet dataset and it's a softmax 1000. So why are convolutional neural network important? I have done a video before for Kera, so you can look at that one, but generally sparse interactions are needed to generate features, which means you don't have to know every pixel of the image. The interactions between few localized shapes is good enough to understand what is in the whole image. And also certain things like, for example, edges, curves and shapes, they all have similar characteristics. So you can share parameters across the whole image to understand what are edges, what are curves and so on. So earlier layers always like finer features like edges, lines, curves, horizontal, vertical and so on. And then the pooling is often used to reduce complexity. These are few features that are that makes convolutional neural network successful. So how do we do this particular convolutional neural network in PyTorch, let's say using MNIST dataset? So we already looked at architecture. So we first define an architecture, how it should be done, and then we implement this architecture in the PyTorch node. So let's go through the code. So as in our template, we are going to first import all the required packages from PyTorch. Then the transform operation is a single operation which converts our input data or downloaded data into tensor form. So, and then we are creating this data loader which will create a batch size of 20, and then we define class names which are 0 to 9. So here I'm showing an example. You can, this is a useful function to label, to show these images as labels. So I'm iterating, so each iteration will get me about 20 images because the batch size is 20. So we are using train loader and we are calling next, so which means there are 20 images and 20 labels. So I'm making a grid of all the images like as shown here. There is a utility function which in tortvision.utils, so I'm using that to generate this image, and finally I'm printing the classes. So you can see each of those classes are described below. So again, the dimension of this particular image is 1 by 28 by 28. So 28 by rows, 28 rows, 28 columns, and the first one is channel. So in some cases you will have 28 by 28 by 1, the way the channel is last, and this is the height and width of the image. So there are a few documentation from PyTorch about the parameters that are used in calling in calling convolution operation, that we will go into it. If you get confused, you can come here and look into it. So let's go back and look at let's look at how to do convolution on MNIST dataset. So here I downloaded the data into local folder. So in this particular, there will be you will create a folder called data, and within that you are going to save these images for both train and test dataset. So we are defining the batch size as 100 and number of iterations as 3000, and you're computing number of epochs based on number of iterations. So again, this train loader which uses data loader, it creates batches of data. We are doing the same thing for test dataset as well. So here is how we are defining our so as we have the general template, we are defining a model ourselves, and within that we are defining the architecture, and we are also defining this forward function. So how are we defining the architecture? Let's look at this. Okay, let's define the architecture. Let's look at our diagram here. So this is what we are following, except the kernel size is 5. So instead of I'm defining this convolution and max pooling operation into one, and this convolution and max pooling operation the second layer. This one is first layer, this one is second layer, and now you are flattening here, and then you are reducing this one into reduce fully connected layers, finally getting to the 10. So we don't be doing all of this one, but let's look at what we did here, how we did the architecture. So in the first layer, I'm defining my in channel is 1, because we have 28 by 28 by 1 or 1 by 28 28 is the image, and then the output channels I'm defining here 32. In the image we define it as 16, whereas here I'm defining it as 32. Then in the second layer, so I'm also defining max pool, kernel size is 2 and stride is 2, and in the second layer I'm doing the convolutional operation with in number of input channel 32, output channel 64, and then the kernel size is 2, right? So then we have a self-dot dropout. Then we are converting this into 1000 layers, and from 1000 layers we are getting to 10. Now if you want to exactly implement that, we can change it to 16, we can change this to 16 and 32, and then kernel size is equal to 3, kernel size is equal to 3, and here we will convert into 1500 and so on. We'll use a couple of more fully connected layers. But so once we define the architecture, we can define forward function, forward propagation step, where we are saying the x is passed through the layer 1, and then whatever the output comes from layer 1, we are passing it through layer 2, which we define here, and then we are flattening here. So this step is done at this stage, and that's what we are changing our output by flattening. And if you use -1, so this one will retain the batch size, and this one will do the flattening step. Then you're passing through the dropout, and then you're doing fully connected layer, and then finally fully connected layer 2. So this is the harder part, and you defined it. So understanding these values is one of the important things when you're defining this. So basically you started with 28 by 28 by 1, and then you're doing max pool with the kernel size true and stride 2. So this will reduce the size from 28 to 14, and from here you're doing one more max pool, so that will reduce from 14 to 7. So you're going to use this, and then finally you get an output here. So model is equal to CurveNet, convolutional net, and step 4, in the step 4 you're going to run this model. So in step 4 we are initializing the model. If we have a CUDA available, then we can run this particular model on GPU. Otherwise we are going to use CPU. For image datasets, it's highly advisable to use a GPU because it's very slow on CPUs. So I instantiated CurveNet here, and then create a criteria cross entropy loss, because we are trying to classify into 10 digits, and we defined our optimizer as Adam optimizer. And here is where we are running our training loop, and so loss is we are storing in loss list. So in this case we are getting the train loader, and this will generate 100 labels because we said batch size is 100 here. So it will generate 100 images and 100 labels, and then we are doing a forward pass of all of those images, and we are getting outputs for hundreds of images, and we are computing a loss for those 100 images, and we are appending this loss. And then finally we do the back propagation, where we initialize all of our gradients, and then we do last and backward, and then we are going to update our weights. Finally we are storing we are actually computing accuracy as we go along, so we're just appending them. So here I'm plotting the loss across iterations, and here is where I'm computing accuracy of prediction. So finally I can say the model as CNN model and CPD. So you can see that the accuracy is going up. In some cases it even went to 100%, but finally I think after 5 epochs it's about 98%. On the test data set, the accuracy about 99.07%. So another important data set that mostly often used for convolutional neural network is FashionMNIST. Instead of handwritten digits, so I can show you, here are some examples of 28 by 28 by 1 images for different items as shown here. So you have a shirt, you have a coat, a dress, pullover, sneaker, ankle boot, t-shirt, and so on. So in order to look at the data set, again we use this Torch Vision data sets and FashionMNIST to download data to local computer in a data folder, and we also created a batch data loader here, for example. and then these are the classes that are available within that particular data set. As before, we defined a image show function, and I'm getting a batch of in this case a batch of 20 values, and I'm printing them here as shown here, and these are the ground truth values. Again, the image size is similar to MNIST dataset, which is 28 by 28 by 1. So here I'm doing training and validation on MNIST dataset. So you download the data in this way, and you download the test data as we have seen before. So these are all Torch Vision datasets, and within that I'm getting this FashionMNIST dataset. So again, batch size is 100, number of iterations is 3000. I'm computing number of epochs based on the number of iterations, and then I'm creating the data loader so that you get every time you call data loader .next, you're going to get a batch of 100 images. So here I'm defining again the same way as I defined before. I defined a convolutional layer with first layer containing count, ReLU, and max pool, and the second layer containing count, ReLU, and max pool. And then drop out, you're doing a fully connected layer, and then again a fully connected layer, finally going from 10,000 to 10. So the forward step is defined here, which is very similar to what we had done before. There is not a lot of differences if you see how the model is instantiated. So in the step 4, we are going to initialize our model that we defined, and then in the we are also going to define our objective function or loss function, and then also define our optimizer function. In the train steps, again we are getting all of those 100 images. We are passing to the forward step of our model and getting the outputs. We are computing outputs, and we know the label, so we are going to get a loss at this step, and we are appending to lossless. And here we are using our optimizer, Adam optimizer, and the gradients are set to 0. We are doing a backward step and updating our weights. And finally, in this case, we are plotting how loss is changing across iterations, and in this case we are doing some tests. We are computing the accuracy. For MNIST dataset, the accuracy is about 80. FashionMNIST dataset, the accuracy is about 88%. It was decreasing until certain point, and it went up again and then decreased. So it's definitely not completely stable. So you could do few more things on this particular architecture to improve it, but I did not try to make it better. Again, so the another important dataset is CFAR10 dataset, and that dataset has 10 classes, and here the dimensions of that particular dataset is different from MNIST and FashionMNIST dataset. So here you have we have color images, and there are 10 classes: plane, car, bird, cat, and so on. So again, the process of downloading is very similar. Other thing to important is to note is our transform step has two tensor as usual, but also have normalize. So this particular normalize is for RGB values. There are 3 channels, and we are normalizing the mean and also the standard deviation in this step. So we are defining here convolutional, instead of defining the layers as we did before. So we are defining conv, where we are defining number of input layers, number of output layers, kernel size, steps, and so on. So the forward step is defined here, where we are defining a ReLU in this step. And finally we have fully connected layer and also fully connected layer, and then finally the output is we get after fully connected layer 3. So we are initializing our model, we are defining our loss function, we are defining our optimizer function, and then running through this example as before. Finally, we are saving the data set as model.stateDict in this manner. So if you want to make predictions, what you can do is, so here I'm defining that IM function. I'm calling the images from test loader, and then I'm using Torch Vision to make a grid, and I'm printing the ground truth. Until here it's good, and this is where we are loading our data set. We are saying model.load dict torch torch load, and then the path that we have saved it. And then generating outputs, model images, and then for each of the outputs you are generating what class label we have, and we are using the predicted value. Here, for example, here predicted will have the label, and using that label we are getting from classes, we are getting the corresponding value. So you can see here I have a cat, ship, plane is the ground truth, and then our predicted value is also cat, ship, and plane. So these are, we looked at three particular data sets. One is MNIST, FashionMNIST, and also C410 data set. But as the image dimensions have improved, and also like complicated convolutional models have started to evolve. So the first one, there are few existing convolutional network architecture that we can reuse. The first one is from 1998, ResNet, which the network depth is 7, and then we have ResNet, the network depth is 8, and people started developing BGGNet, and in 2014 it has about 16 to 19 layers, and Google Inception has 22 layers, and ResNet from Microsoft has 152 layers, and DenseNet has about 121, and FashionMNIST has depending on whether you're using B0 or B7, there are a lot of layers. And MobileNet is another version of the architecture, and you can read the description how this was developed and what is the significance of each of these. These are standard architectures. So BGG16, for example, let me show you how it looks. So these are standard network which are deeper networks and can work on many images. So in this case, a BGG16 looks something like this. You have a convolutional in this first block, you have a convolutional layer, followed by convolution layer, and followed by pooling, and then again convolution followed by pooling, and so on. And the number of convolutions are also increasing in these three blocks, and then finally you have 3 dense layers and you get an output. So this is the BGG16, which actually performed very well in some of the competitions. So so we can clearly define this particular network. Instead of defining all of these blocks, we will first define these two blocks, and then final dense layers as is. So this is a code for defining a BGG network. So in this case, what we did was we defining convolutional 2D followed by maximum max pool, again convolutional 2D, and followed by max 2D. So which is these two blocks. Then we did average pooling, and final step is these fully connected layers. We have one fully connected layer, second fully connected layer, and the third fully connected layer, which has the output 10 values. So in the forward step, because we used SNN.sequential, it is easy to say self.features, and we are naming that particular as self.features. So we will call here as self.features.x, and whatever the output comes here, we are calling self.average pool, and torch.flatten, and then we are passing this x into classifier, which is this particular section code. Everything else is same. We are initializing the model, we are setting the loss and optimizer, we are training the model, and then finally we are evaluating the model. So this particular code look took almost more than an hour on my CPU. As you can see, this is very laborious job. It takes a lot of time. So as the network, as the number of images increases, the dimensions of the image increases, as also the number of convolution blocks are increased, it will start taking a lot more time. It's not feasible to train all the time. So and so there is a concept known as transfer learning, which we will discuss now. So let's look at in this case there is an image, and we are passing through convolutional network, and we are doing a max pool, and there is another this is the architecture of ResNet. So then you have a convolutional block which is repeated. This particular whole block is repeated 3 times, and you have a stage 2 which is repeated 4 times, and stage 3 which is repeated 6 times, and finally stage 4 which is repeated 3 times. All of these will become a ResNet 50. You can see this is really long. The depth is about 50 layers or so, so which is very hard to implement on a CPU and even in a GPU. So the way to use these kind of models is some larger companies like Google, Facebook, and others who have a lot of infrastructure. They will train a model on well-known standard datasets like ImageNet image datasets, and they will we can store the weights from that model. For example, ResNet will have certain weights when trained on ImageNet datasets. If it's trained on some other standard public datasets, it will have corresponding weights available, and you can load them the computed or pre-trained model weights into your current model, and then you can use those weights to train on your own datasets. So what happens in most of the transfer learning operation is, as you know, the earlier part of transfer learning involves learning edges, learning curves, learning smaller shapes, and so on. So you don't have to really change those parts. Whatever image it have, you have edges, curves, shapes, some kind of a broader shapes, and so on, right? So all of these earlier layers will learn those features, and the final whatever image it is, all of those images have these particular features. So in the end, the last layer is when you are actually trying to look at the broader picture and trying to classify into one of your classes. So instead of changing everything, you can keep all of the weight constant, and you only change the weights of the final layers. You can define which layers you want to change, and then for example, you can freeze all of these layers, but you can change all of these weights to brand new weights based on your new dataset, your current dataset, and compute in the classes. So most often all your convolutional layers are frozen, and then the fully connected layer or the final layer is often changed to reflect your own classes in your dataset. For example, you can start with a ResNet dataset that is trained on ImageNet, and then that ResNet architecture can be used to classify a CFAR10 dataset. So we will look at an example. There is a little bit more explanation on what is ResNet architecture code. I did for Keras examples before. I can paste this link in the video section, and also I did transfer learning an end-to-end example with lot more detail than what I'm specifying here. This particular course is only to learn PyTorch code to do various types of neural network operations. So you can see the code here. So device is, whether you want to use CPU or GPU. ResNet, like this is where we are loading our previous dataset. So model start ResNet 50. There are quite a few important predefined networks that we can train, and pre-trained is equal to true. So we are loading all of the models. And what we are doing here, we are saying freeze all layers in the pre-trained network. So we are not going to compute gradient all the way back to the starting step. We are saying requires for each parameters in ResNet parameters, we are saying requires grad is equal to false, which means you won't compute gradient or you won't update their weights. Then in the final layer, we are that's where we are changing. So we are taking ResNet dot fully connected layer, and we are taking these features that are in the final fully connected layer and passing it to 10 layers. And then so remember that this particular ResNet data is trained on ImageNet data, whereas we are trying to generate, which has 1000 classes, but we are trying to generate 10 classes. So we are taking 1000 features from the last layer, and then we are feeding it to one more fully connected layer and generating 10 classes. So but at this step we already have our model, and then now we are defining cross entropy loss, we are defining optimizer. We are saying we are only training fully connected parameters. Everything else, I think because the gradient is false, we are not computing anything more. Again, there are few steps here because we are using ImageNet data has a dimension of 224 by 224, whereas our data set has I think it's 28 by 28. Yeah, CFAR10 dataset is 32 by 32. So we are resizing that image, enlarging that image to 24 by 24 because our ImageNet data is 224 by 224. That's first step, and then the second transformation is we are converting into tensors, and because these are RGB values, we are normalizing them for each channel at the mean and variance. So we are downloading our training data set, and we are then applying those transformations. So the training process is very similar to what we have seen before. We have defined optimizer, we have defined our cost function. We are using ResNet 50-hour model and passing our inputs. So ResNet model is already defined. So we are doing this backward step, and this backward step will only compute the final layer weights. So once everything is finished, you can save your final ResNet as your ResNet CFAR10 path. So here I am trying to load, but it's taking a long time. I think ideally you would want to use a GPU to compute this. So I was trying, this is the prediction code. Again, you can get the test loader, you are getting some images and then you are predicting them, and then you can print corresponding image as well as the predicted class. So I'm not going to go through the description of how transfer learning results are, because I needed a GPU to run this one, and to run this particular transfer learning on a CPU is taking too long. So let's look at what we looked at today. We looked at convolutional neural network. We looked at how this can be run on MNIST dataset, FashionMNIST dataset, and also CFAR10 dataset. We also understood there are various standard networks that can be used. By default, bigger companies have already trained, and the weights are made publicly available. We can use those weights, and we can do a task of learning weights for our own data sets. The reason being, images have some the features that are learned in earlier stages of images are similar across different datasets and different problems of images. So we looked at the code of transfer learning. Essentially, we are looking at a ResNet model. So in transfer learning, we are loading one of the well-known models, and we are freezing all of the earlier layers, and we are taking the output from the last layer and feeding it to another fully connected layer, and we are mapping them to 10 output layers. So the output from here, these weights that are coming from 1000 classes to 10 classes, is what we are learning here. So here is a list of frequently used pre-trained models, and you have ResNet, you have VGG16, Inception v3, DenseNet 121, and also you can download FashionMNIST, and there are like B0 to B7, and use them in training your datasets, your own datasets.